Moving into chapter 7.3, we begin to study multivariable linear systems. So far, we have studied systems of equations that involved a maximum of two variables. Here, we are going to look at solving linear systems of equations that have three variables or three unknowns. It is important to note that a system can only be solved if there is a distinct equation for each variable. In other words, a system with three variables will require three distinct equations. A system of four variables will require four distinct equations. A system of five variables will require five distinct equations, etc. All right, so on and so forth. So if we had 100 variables that we were trying to solve for, we would need 100 distinct equations in order to solve. Now, I'm not going to ask you to do more than three, right? And again, as I just said up here, in this section, we are going to be studying linear systems with three variables. So here are your steps for solving a three-variable linear system. Step number one, use substitution and or elimination to solve for a single variable, if possible, or to create a two-variable system of equations. The goal is to simplify the system, all right? So you're going to be using a combination of substitution and or elimination to begin to simplify the system down. If you can solve for a variable right off the bat, that's great. If not, see if you can turn your three-variable system into a two-variable system by using elimination or substitution. 2. Continue to use substitution and or elimination to solve the simplified system that we created in step 1. Once two variables have been obtained, back substitute the values into an appropriate equation to solve for the final variable. Generally, that's going to be one of the given initial equations, right? Back substitute to solve for the final variable. And finally, check that the solution satisfies each of the original equations. So just like we were able to check our work by plugging in our values in our two variable systems, we can do the same thing here with our three variable systems. Let's look at an example. Solve the multivariable linear system. And if you're wondering why we call these linear systems, it's because the degree or the power of each variable is 1. Here, we have x minus 2y plus 3z is equal to 9, y plus 3z is equal to 5, and z is equal to 2. So notice that we have three variables in this equation. The good news, here we already know that z is equal to 2. We can easily substitute that value into the second equation, and doing so will allow us to solve for y. Notice that our second equation here only has y's and z's, so if we plug in 2 for z, that's going to give us y. Y plus 3 times 2 is equal to 5. 3 times 2 is 6. Y plus 6 equals 5, which means we subtract 6 from both sides, giving us y is equal to negative 1. Now that we have y and z, we can solve for our final variable x, and we can do so by back substituting in our values for y and z in this first equation here. Okay, back substitution to solve for x. This gives us x minus 2 times negative 1 plus 3 times 2 is equal to 9. Well, negative 2 times negative 1, that's going to become x plus 2 plus 6 is equal to 9. 2 plus 6 is 8. So if we subtract 8 from both sides of the equation, we get x is equal to 1. And there we have solved for each one of our variables. Now, to write our final answer, we are going to write them as the ordered triple x comma y comma z. 1, negative 1, 2. Again, we can verify our solutions by plugging the ordered triple into each of the original equations. Plugging in for x, y, and z in each one of these original equations will make each statement true.